In this class, we're going to look at how JavaScript can be used for user input validation. JavaScript can be used to ensure that the information provided by a visitor to a website conforms to some specification. Now, very often when a user inputs information into a website, it's possible just from looking at it to see that it's just made up and that it's not valid. And that's very useful in two ways. The first way is that the web page can immediately tell the user that they've made a mistake, so they can get feedback very, very quickly. And that saves the user time. It also saves resources at the server end because the server isn't processing data that's not going to go anywhere. It's not trying to process data that's useless. Without this input validation, all of the data would be sent from the web page back to the server, and the server would spend time trying to process it, and then it would send back a message saying that had failed back to the web page. But validating the data within the web page is going to save time and resources. Imagine for a moment that you are at some really trendy bar where all the beautiful people are, and you meet this very attractive person and you spend a lovely evening together. And this very attractive person says to you, "I have to go now, but I had a really, really nice time and I'd love to meet you again tomorrow. So here's my phone number and give me a call and we'll go and have dinner or something." So imagine the very next day you take out the phone number and you see that the number the person wrote down was 082 7445. Well, with that phone number, you're not immediately going to rush out and book the most expensive restaurant in town. That's because that number is made up. So how can one be so confident that the phone number provided in the bar by the beautiful person was fake? Well, for starters, we know that in Ireland, mobile phone numbers start with a 0, followed by an 8, and then the next digit is usually an indication of the network. So we have 087, 086, 085, and 083. We used to actually have 088 as well, if you're old enough to remember that, but that was for the now defunct analog system. So the fact that the number doesn't start with 083, 5, 6 or 7 is a dead giveaway. It's also a bit short. We know that the mobile phone number should be 10 digits in total. So that's how we can tell that this phone number is fake. So let's look here now at this JavaScript code that validates an Irish mobile phone number. We start off by declaring the variable mobile num, and that's going to hold the number input by the user. We have a variable valid that we're going to use to store a Boolean variable that tells us whether the number is valid or not. In this line, we're creating the new Boolean variable and we're assigning it a default value of true. So without doing anything else, this variable valid will be true. Now what we're going to do once we've input the number is we're going to see if we have any reason to change our minds about the validity of this number. So we're going to assume the number is okay, and then if it fails to meet one of our requirements, we're going to set valid to false. But of course first we need the number. So here we say mobile num is assigned prompt, and then we have please enter your mobile phone number. So that's the prompt that's going to appear in the dialog box. And there's also going to be a default number inserted. Inserting a sample number like this is usually a very good idea because it gives the user an idea of the format that you're expecting. On seeing this here, for example, the user knows that the number is expected to be in the 10-digit format with the leading 0. Without this hint, they might be tempted to also use the country code and give plus 35387. So if ever you're prompting the user for something in a web page, it is a good idea to give them an idea of the syntax that you're looking for. Someone who was born in 1980, for example, might be very used to writing their birthday the 1st of the 1st, 80 instead of 1980. So in that situation, you might also want to give some sort of a hint. So let's go to our first test here of the number now that we have it stored in the variable. The variable mobile num is neither a string nor an integer. JavaScript is very flexible when it comes to things like that, but we're going to be using it as if it was a string. If the prompt box is closed by the user, then the prompt will return null. So we want to check that that hasn't happened. We also want to make sure that there's actually something inside in the string. It may be that the user has deleted the hint that we gave them, but hasn't replaced it with anything else. So in that case, the string would be empty. Now, a null string and a string with nothing in it are not the same, so we need to check for both of those. So here we're saying if the string is null, or if the string mobile num is empty, then we want to set valid to false. So that's the first test we're applying to the string. And if it fails that test, we assign false to valid. Now the next test on the string is one for length. We want to make sure that the string is 10 characters long. So here we use the length method, and we're saying if mobile num.length is not equal to 10, then valid is assigned false. So if the string doesn't have 10 characters in it, it's not a valid number. Now the next thing we want to check is that the string begins with 08. All Irish mobile phone numbers begin with 08. So if it doesn't begin with 08, there's a problem there. Here we're using the slice method. Okay, now slice takes two parameters. The first parameter is where we want the slice to start, and then the second parameter is actually where the next slice would start, so it's off by 1. So this tells us here we want a slice that starts at 0 and then has 1 as its end. 2 would actually be the start of the next slice. That's the way it works. So slice can be a bit confusing. This is not saying start at 0 and give a string with 2 characters long. It's tempting to think that given the context, but that's not what's going on. 0 and 2 are the start and end points of the slice. So if this slice is not equal to 08, well then the number is dodgy, and so we set valid equal to false. So the next thing we want to do now is we want to check that the third digit in the phone number is a 3, a 5, a 6, or a 7. If it's not one of those, the number is dodgy. So we're going to extract out that third digit from the string, and we're assigning it to a variable c. So we're saying c is assigned mobilenum.slice, and the start point is 2 and the end point is 3. So this gives us just a string with 1 character, and that'll be the third character in the string. Remember, the first character in the string is at position 0. So it's 0, 1, 2. That can sometimes cause confusion, but remember, all arrays in JavaScript start with 0 as the first element. Now look at the structure and the syntax of this condition here. Now that's actually the exact opposite of what we're looking for. But if we put the asterisk in front of that to do a not, then that gives us the condition that we want. So if it's not 3, nor 5, nor 6, nor 7, then the number is dodgy. Sometimes it's easier to specify a Boolean expression for the exact opposite of what you want, and then slap a not in front of it. Now the next portion of the code is going to do something that we could have considered doing much earlier, and that it's going to check that every single character in the string is in fact a digit. So far we've established that it's 083, 085, 086 or 087 to start, and we know it's 10 characters long, but we don't know that the last 7 characters are actually digits. So the number could be 087 ABC DEFG, and it would still be valid up to this point. So the next portion of the code is going to go through the remainder of the string, character by character, making sure that each character is a digit and not a letter or not anything else. Now this precludes the possibility of using that American custom of substituting letters for numbers in phone numbers, to make them more memorable. So here you couldn't have 087 big dude. Now we have a loop here that's going to loop through the remainder of the string. It's going to count from 3 up to 9, incrementing by 1 every time. So this loop is going to continue as long as n is less than 10. Now when n is equal to 9, it will be less than 10, so that'll be okay. It'll do that iteration. But when n is equal to 10, this condition will be false, and so that iteration won't happen. So in counting from position 3 to position 9, we're actually going to be looking at the 4th, 5th, 6th, 7th, 8th, 9th and 10th character of the string. But remember, character number 1 is in position number 0. So we're going from 3 to 9. Now inside in this loop, n will be 3 or 4 or 5 or 6 or whatever, okay? We're going to put into C a single character. So just like we did before, we're going to use the slice and we're going to put the nth character into C. And then we can perform tests on C to see if it conforms with our requirements. Now, if C is less than character 0 or it's greater than character 9, then it's not a digit. Now, we have to be careful here because we're dealing with digits. It's tempting to treat them like integers. But here we're interested in the value of the string. And if that value falls below 0 or above 9, then it's not a digit. So in that situation, we're going to put false into valid. So we've input the number and we've made it jump through a series of hoops. And if it fails at any one of those points, we concluded that the number wasn't a valid phone number. Of course, this still doesn't stop someone just making up a number. But now if they make up a number, it at least has to look like an Irish mobile phone number. But beyond that, there's no way of knowing if the number's made up or not. Only the phone companies could figure that one out. It's sometimes possible to come up with a set of rules for some data that help you detect if someone has actually made it up or not. Suppose the telecoms regulator decided that a shocking number of people were giving out fake phone numbers in bars to hopefuls and that something had to be done about it. Well, one thing that could be done is that you could use the last digit of the phone number as a checksum. Now, a checksum is a digit or number of digits that don't actually do any work in the number apart from verifying its validity. So you could use the last digit of the phone number as a checksum and decide that the last digit should always be equal to the number of even digits in the rest of the number. So a number like 087 999 666 would have 5 even digits in it up to that point. And so then the last digit should be 5. So the number would be 087 999 666 5. Remember, 0 is an even digit as well. Now, if someone entered this number then incorrectly as 087 999 9665, we'd know that something was wrong because the first portion of that number has only 4 even digits. But the checksum is saying there should be 5. So something has gone wrong somewhere. Now, a checksum like this isn't very sophisticated. It wouldn't catch a scenario, for example, where numbers are transposed. So if you had 078 999 666 5, that would appear to be okay. Now, one of the most useful scenarios in which we use checksums on a website is to check the validity of credit card numbers. So hundreds of thousands of credit card numbers are entered into websites every day, and people are bound to make mistakes. Now, the sooner you can detect those mistakes, the better. It's less frustrating for the user if they can be told straight away they've made a mistake. And of course, it's cheaper for the website and for the banks if you don't have to waste time and resources processing numbers that aren't valid. Now, in a 16-digit credit card number, the last digit is a checksum. And so if this checksum doesn't come out at what it should be, you know there's a problem with the number. Now, of course, just because the checksum is valid doesn't mean that there's enough money in the account to make the purchase. And it doesn't mean the card isn't stolen. All of that still has to go through the clearing bank to check that everything is okay. But if the checksum is dodgy, you know there's no point in sending all that information to the bank. And that's the real benefit of checksums. It lets you do sort of a pre-screening straight away to make sure something isn't totally made up. So 16-digit credit card numbers use a Loon formula. And the checksum is calculated as follows. Starting with the second last digit, you work backwards towards the front of the number. And you multiply every second digit by 2. Then you add all of the resulting digits together. So then you add all of the resulting digits together with the unmodified digits and the checksum. And then the resulting number should be evenly divisible by 10. If it's divisible by 10, then the checksum was valid. If it's not divisible by 10, then you have a problem. So let's take a look at this number here now that I've made up. It's 4499228308017422. So starting with that second last digit and moving towards the front of the number, we multiply every second digit by 2. So 2 becomes 4, 7 becomes 14, 0 gives us 0, 0 gives us 0 again, 8 gives us 16, 2 gives us 4, and 9 times 2 is 18, and 4 times 2 is 8. Now we add up all the resulting digits. So when that 9 was multiplied by 2 and gave us 18, for example, that 18 becomes 1 plus 8, which gives us 9. The 8 times 2 giving us 16 gives us 1 plus 6 gives us 7. So we're adding up 84994273 plus 0801544 and 2. And this gives us a total of 70. And 70 mod 10 gives 0, which means the checksum is valid, because 70 is evenly divisible by 10. Now what I would like you to do as an exercise is to pick one of the digits in this credit card number and change it to a different digit. So you could, for example, take the first 9 there and change that to a 6. Apply the same algorithm to the new number and you should get a result that isn't evenly divisible by 70. However, what makes this technique so sophisticated is that it'll give you an error if two numbers are switched. So if you had 44992928, the transposition of those numbers would be detected as an error. That wouldn't have happened with our very simple telephone checksum. Now, checksums aren't infallible, of course. And with the credit card number, you've only got one digit to use as a checksum. If you wanted your checksums to be more sophisticated, you could use more digits, of course, and have a more complex system. And of course, checksums don't protect you from fraud. If the way you calculate your checksum is kept a secret, then it might provide some sort of security. But really the purpose of a checksum is just to catch someone making a mistake when they're typing in data. Now, it turns out actually that we can tell quite a lot about a credit card from just the number. All Visa cards start with the number 4, and Visa cards can have a length of 13 or 16 digits. Now, I've never seen a 13-digit one myself. American Express cards start with 34 or 37, and they're 15 digits long. Now, the same algorithm is used on American Express cards. In fact, that's why we specify the algorithm as starting at the end and working forwards. MasterCard start with 51, 52, 53, 54 and 55, and they're 16 digits in length. Discover is a card you see in the US. You don't see it much in Europe, really. It starts with 6011. And then Diners Club has a range of sequences as well. And that's 14 digits. So this information could also be used to help verify if a number was made up or not. That's why websites ask you whether you're using Visa, American Express or MasterCard. They could actually tell from the number what you're using. The International Standard Book Number, or ISBN, is another everyday use of checksums. Every book has a unique number that identifies the publisher and other information. So each book has its own unique number. So if you want to tell someone about a great book and you want to be sure that they get the exact book you're talking about, you give them the ISBN and then they can just order it from that. The last digit of the ISBN is a mod 11 checksum. Now we'll see in a while where that mod 11 comes from. ISBNs are 10 digits long and the last digit is the checksum. Now in this example here, we can see how the ISBN is calculated. We take the first digit and we multiply it by 10. We take the next digit and we multiply it by 9. We take the third digit and we multiply it by 8. The next one by 7. The next digit by 6. The next digit by 5 and by 4 and by 3 and by 2 and by 1. Now all of these products are added up to give a grand total. If that total is evenly divisible by 11, then the checksum was valid. If it's not evenly divisible by 11, then the number wasn't valid. Now this mod 11 is in fact a bit of a problem though, because it may happen for this to work out that you need the last digit of the ISBN to be 10. Not 0 now, 10. If you're using 0 to 9, you have a problem. So some ISBN numbers will have X as the last digit. And that X stands for 10, as it did in Roman times. So in this example here, when the last digit X is multiplied by 1, it gives 10. And here 242 mod 11 is 0, so the number is valid. This idea of seeing if one large number is evenly divisible or not by another smaller number comes up a lot, and we use the modulus function to work that out. Now, I don't want to go into the whole theory behind modulus checksums, but there are a few general rules that can help. In general, the modulus number chosen needs to be greater than the number of digits in the number and needs to be greater than the range of any single digit. So we have the mod 11 checksum in the ISBN, and the ISBN number itself is only 10 digits long. And there's no digit in the ISBN number that goes up to 11. Prime numbers work especially well for the modulus. So you see 11 and 23 an awful lot. If you make up a random ISBN number, you have about a 90% chance of the checksum actually catching that. In fact, it's 10 out of 11. So that's a pretty good checksum. Republic of Ireland PPS numbers, used to be known as PRSI numbers, they use a mod 23 checksum. Every person working in the Republic of Ireland has a PPS number, be they Irish or not, and all children born in Ireland are now issued those numbers at birth. Actually, it turns out that the number of organisations that can actually ask you for your PPS number and that are legally allowed to store it is quite small and very controlled. But that's actually a conversation for another day. It's not relevant here. The PPS number is 7 digits followed by a checksum letter. So you might have 1, 2, 3, 4, 5, 6, 7, P, for example. Now, we'll see after whether P would be correct there or not. So let's look at this PPS number here. The number is 6059922. And we're going to work out what the checksum letter should be. Although this algorithm is different from the ISBN number, you can see there's the same kind of process at work. Here the first digit gets multiplied by 8, the next one gets multiplied by 7, the next one by 6, the next one by 5, and by 4, and by 3, and by 2. We take those products and add them all up together for a grand total. And then we do a mod 23 of that total. And in this case, that gives us 8. Then we use a table to see which letter goes with that number. So 1 gets A, 2 gives B, 3 gives C, and 4 gives D, and so on. So a mod 23 value of 8 will give a checksum letter of H. Now, it turns out that the PPS numbers in Ireland do come with a bit of historical and cultural baggage. For many, many years, married women, when they were assigned numbers, were given the same number as their husband, but with just an W after it. So some PPS numbers have 2 letters at the end. The first letter is the checksum, and then the last letter is W for wife. That practice has been discontinued, but of course, many people still have those numbers. Euro banknotes use checksums for the last digit of the serial number. Now, the first digit of the banknote is a letter, and that letter tells you the country that the banknote was printed in. Anyway, whatever about where the note came from, you convert this letter to a number. So A gets 1, B becomes 2, C becomes 3, and so on all the way up to Z gets 26. So X, for example, will be converted to 24. So you add this number and all of the other numbers up, and then you add the digits together. And you keep adding the digits together until you only have one digit left. And that digit should be 8. If it's not 8, then the checksum wasn't correct. Now, just for the crack, I went trawling the web for other examples of checksums. And in Finland, the equivalent of the PPS number is the SOTU. Now, I won't even try to pronounce what it stands for. The number there is a lot less random than in Ireland. In Finland, the first 2 digits represent the day the person was born, the next 2 represent the month, and then the last 2 digits represent the year. As we saw with the Y2K problem in 2000, using just the last 2 digits to represent the year can be problematic. Rather than use 4 digits to specify the year, what the Finns have done is they have a separator that comes after the year. If you were born in the 1800s, this will be a plus. If you're born in the 1900s, like 1980, that'll be a minus. And if you were born in the 21st century, that'll be an A. The next 3 digits then are what makes the number unique. The third of those is even for females and is odd for males. This means actually that at most 500 men could be born in Finland on a given day before this system would break down. But actually the birth rate in Finland isn't so high that that becomes a problem. The last digit then is a checksum. To calculate the checksum, the separator is ignored, and all the remaining digits are treated as one large number. You do a mod 31 of that number. Notice again that 31 is a prime number. That number then is mapped to the checksum. In Ireland it was a mod 23, so the checksum mapped comfortably to a letter. However, there aren't 31 letters in the Finnish alphabet, so they use digits as well. 0 will give you 0, 1 will give you 1, 2 will give you 2, and 3 will give you 3. But 10 would give A, 11 would give B, 12 would give C, and so on, all the way up to Y. Now, lots of other countries use checksums as well. In the UK, they use checksums. In the People's Republic of China, there's a checksum. It's a mod 11. In Italy, you could nearly tell what someone's mother had for breakfast the day they were born based on their number, and that's a mod 26. The US and Canada share a numbering system, but only Canada uses checksums. Many barcode systems use checksums as well. In the Republic of Ireland, a student's CAO number, which very often ultimately becomes their college ID number, also uses a checksum, but the way that checksum is actually calculated is a secret. So to get to grips with checksums, you can try some experiments. Take a number that you know is valid, apply the algorithm to it and see how it works, and then change one of the digits, apply the algorithm again and see that it doesn't work. So you can do that with your credit card. You should be able to do that with your PPS number. You could also take out some banknotes and try that. The ISBN algorithm and the credit card algorithms are very common because, of course, those numbers are used globally. And the ISBN is unusual because sometimes there's an X at the end. Some of these algorithms are more difficult than others to code in JavaScript.